Well, definitely the hardware has taken leaps ahead of where the software is. And I think software, we've always had problems in the software industry, but I think we're starting to see the cracks in the software industry because of multi-core. Problems that we've had, they're just being highlighted now. The difference is companies like AMD are proliferating multi-core using the x86 architecture. And so it's kind of multi-core for the masses. Scientific and academic users have been facing these problems for years. In fact, they kind of chuckle, when they hear about all the multi-core revolution because they've been doing this for 10 years, or maybe even more. But the difference, again, is the commoditization of it and kind of how does software make that leap across that gap to bring this to the masses, bring it to people, to everyday sort of business types of processing that they can take advantage of it. Another thing that really is changing also is what you might call revenge of the SMP. We see over the last few years a movement towards grids. But now with SMP hardware, with multi-core hardware, you have 16 32-way machines that are very inexpensive. So I think you'll start to see a lot of conglomeration and processing on those types of machines. Virtualization is very important, and we've seen just a huge takeoff with virtualization. And again, they're taking advantage of those multi-core machines so that they can take multiple boxes, shrink them down into one box, a lot less cooling, a lot less electricity. It saves data centers a lot of money. Well, programming models, even within Java, for parallelism, are fine-grained. I think we'll start to see other programming models, maybe one such as the one we see in Erlang, where you have lots of very lightweight threads that communicate using message passing. That's a very good construct that we may start to see built into other languages such as Scala. Again, this is a language built on top of the JVM. We have quite an investment over the last several years in JVM and Java technology, and we definitely don't want to throw that away. The JVM, we've seen every release, it gets better and better. New functionality, but also better performance. The memory model in Java 5 was excellent. The Java Util concurrent library within Java 5, again, excellent. But these are building blocks I think we can build on top of. And I think that's great because there are millions of Java programmers out there. Let's take advantage of the constructs that we have and build on top of it. So the message really, I think, is don't throw away all of the advances that we've made in the last few years in Java, and especially JVM technology. I think these are building blocks that we can build on top of. And we'll start to see higher level abstractions built on top of those building blocks that we'll be able to utilize and go forward with. There always has been a perception in the industry that Java doesn't perform well and that it doesn't scale. But whenever someone brings that opinion to me, I always ask them, well, where did you get that perception? And they'll say, well, 5 years ago, 7 years ago, we ran some benchmarks. So what I would tell them is you need to go back and run those benchmarks again, because we've shown with the Java framework that we have, based on data flow concepts, that Java definitely does scale. And we've shown it scale up to 32 cores. So we're very excited about that. The type of applications that I work on are very data-intensive types of applications, which means they're very memory-intensive. And what we've seen with the AMD Opteron platform, especially with its hypertransport architecture, is that it really provides a platform for very memory-intensive types of applications like we have. The benchmarking that we've done on the AMD platform shows that it is extremely well-suited for those types of applications. And we feel very comfortable with it and very excited about the capabilities that it brings to bear. Also, AMD has Code Sleuth, which is a software product that's open source. What it allows you to do is to equate hardware events to your Java code. Now, Java's always provided kind of an abstraction layer on top of your hardware, which means you get sort of separated from it, which is one of the complaints from the people who work in C or C++. They're more bare metal. They have easier access to the hardware. And so I think combining all these together, what we're seeing today is that scalability in Java is not just a possibility, it's a reality. An excellent real-world example that we've run into recently, we were working with a customer. They were actually using DataRush, the Java platform that we provide that uses data flow technology. They were using it to do some deduplication of data. And they had millions of rows of output from that process. And they decided to take that data, load it into a relational table, and then do some SQL queries against it to generate a final output that they wanted. The job that they created ran in about 3 hours. And when we talked to them about it, they were actually very happy with that performance. So when we heard that that's what they were doing, we asked them, let's take a look at it, and we'll do the same thing using DataRush. And so we did. We ported their SQL basically to Java, ran it within the DataRush framework, and it ran in 22 seconds. So 3 hours, 22 seconds. That's transformative. It's like the difference between me walking to New York versus taking a jet. That gets people thinking in a different direction because they start thinking about things that they couldn't do before. Now, does that say SQL is bad? Absolutely not. SQL is great. It was meant for certain things. It was not meant for the job that they were doing. What we were able to do is take advantage of all 8 cores on that machine, make one pass through the data. It's a 490x improvement. That's huge. So if you wanted to learn more about that, you can read about it in Java Development Journal. It's in their March issue. It's an article called 1 Month, 1 Team, 1 JVM. And I think that's very important to focus on. It was 1 JVM, taking full advantage of the full machine, not just parts of it. We didn't virtualize the machine. We used the whole thing. So come by our booth. We're here at JavaOne. Hope you enjoy your experience, but stop by the pavilion and talk to us about it. Well, as a Java professional, I think to prepare yourself, you really should start investigating all the talk that's going around about different programming models that are being developed. Also, there's languages such as Scala that are being built on top of the JVM, JRuby, Groovy. I think it's interesting to go and learn about those and kind of see where the JVM is going in the future. I think JVM is a great platform that we'll continue to build on for years to come. In Java 7, the fork join construct is being added. Again, very interesting. Great building blocks that we can build on. And also start learning new techniques. From these other programming models, you may learn things that you can actually then take into Java, new patterns of parallelism that you can apply to Java to keep it going forward. So I think it's also important to learn those finer grained parallelism constructs and learn how to use them. If you're so inclined, it would really help you as higher level abstracts are built on top of them. Understanding kind of the programming, the model underneath it, always helps you write better code on top of it. I started out life as a C and a C++ programmer. Eventually, made the leap to Java. Very happy that I did. But I think that experience helped me be a better Java programmer because I understand kind of what's going on underneath. I understand a little better about how my code is affecting the rest of the system, having that experience before. So I think it's always good to dive down deeper. Even though you may not live at that deep level, it helps you understand, living at the higher abstraction level, kind of where you are and how to take advantage of it and how to write better code.